All right, hello everyone, and welcome back to another video. This one, we're going to look at a thermochemistry example. So we have been talking about thermochemistry in class. We've done a couple of examples, but this one will be just sort of a very basic manipulation of a thermochemical equation. This is the question we are going to look at. It's question number 2. In your workbook, it's on page 17, I believe. All right, so we're going to start off with our thermochemical equation, the one that's actually given in the question. Magnesium plus oxygen produces magnesium oxide, and the delta H for that reaction is negative 1204 kilojoules. So the first part of this question is asking, is this reaction exothermic or endothermic? And the giveaway here, the thing that's going to let you know that, is the delta H value. A negative delta H value is an exothermic reaction, okay? So part A question, exothermic. If that was a positive delta H, it would be endothermic, right? So easy enough for that one. The second part of that question wanted to know how much heat was transferred when 3.55 grams of magnesium react at a constant pressure. In your chemical equation, in the thermochemical equation, we don't have grams, of course. We have moles, right? 2 moles of magnesium. When they react, it will release 1200 kilojoules of energy. But again, I don't know how many moles right now 3.55 grams is. So I have to change that value to moles first before I can use my thermochemical equation and interpret how many moles are associated with that much heat transfer. So 3.55 grams, I'm going to change that into a mole value, so mass divided by molar mass. 3.55 divided by the molar mass of magnesium, so get this from your periodic table. This gives me 0.146 mole. Right? I can set up a very simple cross multiply here. So 2 moles of magnesium releases 1204 kilojoules. You can see that I've got that here. I don't have 2 moles, however. I have 0.146 mole. So I want to know how much is released for that particular amount of moles. Set this up as a little ratio, cross multiply, and you figure out that X, the number of kilojoules released from the 0.146 moles, is negative 87.9. So again, negative because this is exothermic. It's releasing 87.9 kilojoules of energy. Pretty straightforward again. Nothing too fancy. We've done lots of mole and mass calculations, so that should be nothing new for everybody. Part C of that question is similar again. Wanted to know how many grams this time of magnesium oxide were produced when an enthalpy change of negative 234 kilojoules occurs. So I'm going to just move my paper up here so you can see this a little bit better. There we go. So same idea. I only know moles from my thermochemical equation. So 2 moles of magnesium oxide, when that is produced, it releases 1204 kilojoules. That's what I get from my equation. But again, I don't know how many moles are being released from 234 kilojoules. Obviously, it's going to be a bit less, right? 2 moles will release 1200, so I'm expecting quite a bit less if I'm only releasing 234. Set it up again and do a little cross multiply, and you figure out that X, the number of moles that's released with 234 kilojoules, is 0.3887. I'm keeping kind of an extra sig fig here. I don't want to round anything because I do want to know grams. The question C wanted to know how many grams. I can only initially interpret moles because that's what's in my thermochemical equation. It's a mole-based equation, of course. 0.3887 moles. What is that in grams? So I'm going to change that into a mass value, moles multiplied by molar mass, so 3.887, multiplied by the molar mass of magnesium oxide. Get this from your periodic table again. Magnesium plus oxygen, so 40.3044. And I find out that the number of grams is 15.7 grams of magnesium oxide. Both B and C in that question, very similar calculations, okay? Very, very similar. Part D, also very similar as well. So here's part D. This one How many kilojoules of heat are observed when 40.3 grams of magnesium oxide are decomposed into a constant pressure? So this time I'm looking at the product and I want to know the opposite direction. I want to know something about the reverse reaction. So in the forward direction, magnesium and oxygen produce magnesium oxide. That's exothermic. The reverse is going to be the opposite. When magnesium oxide decomposes into magnesium and oxygen, that's endothermic. So I'm going to set up the same kind of ratio without the negative sign on my delta H this time, because it's the opposite direction. It's endothermic and not exothermic. Okay, again, I'm starting with a grams, 40.3, but I can't do anything with grams because my thermochemical equation, like all equations, are mole-based. So 40.3 grams, changing that to a mole value, mass, divided by molar mass, 40.3 divided by the molar mass of magnesium oxide, which coincidentally is 40.3044, so almost exact. The number of moles is going to be 1. Okay, 1 mole. Then I do my cross multiply again. So 2 moles of magnesium oxide, when that decomposes, we've got 1204 kilojoules. Notice that this is positive now. There's no negative sign here because we're going in the opposite direction. It's endothermic. All right, so 2 moles will require 1204 kilojoules. How many kilojoules are required for only 1 mole? Well, half as much, obviously, right? But you can cross multiply, you can figure this out, and we'll find out that it's 602 kilojoules of heat absorbed when 1 mole of magnesium oxide decomposes. Endothermic, opposite direction of our initial reaction. There's a couple of more examples like this in your workbook and done very similar, where you've got to do some mass and moles calculations, a little cross multiply to figure out your ratios. And I would suggest that you give those a try. And of course, as always, if there's any issues or problems, you can let me know. Email me, you can ask in class, or you can check the solutions online for all of these questions. Good luck, and again, let me know if you have any issues. Thanks for watching. Bye.